Hello Year 12 and welcome to our second video for continuous probability density functions. In our first video we revised some of our work from Year 11 to do with discrete probability distributions and stats. We calculated mean, variance, standard deviation. We also had a look at relative frequency and how to use that to calculate mean, standard deviation as well. This time we're going to look at continuous distributions. Now, with a continuous distribution, if I choose any two values, there's always some other value in between. So it's not something I count like how many rainy days, but typically something I measure like how much rain fell or how long will it take for something to occur. So, here's an example. The district line is at the London Underground, and I'm making a lot of this information up, but let's just say trains depart Acton Town station for the city every 10 minutes. So, no timetable, just turn up. I know that every 10 minutes a new train leaves the station heading towards the city. So, I could turn up and the train leaves straight away, or I might have to wait up to 10 minutes. But I won't wait any more than 10 minutes, and I won't wait any less than 0 minutes, that's pretty obvious. But I could wait any value in between. It could be, 3 minutes, 4 seconds, 4.2118 seconds or something like that, whatever. Continuous values between 0 to 10. Could be any length of time between 0 minutes and 10 minutes. And this makes it a continuous probability distribution. We had a go at doing these in the previous video by grouping the data, and I could, if I liked, do that here as well. I could look at the probability of the train arriving in the first minute, second minute, third minute, and so on. I could do that, but I want to be a bit more precise than that. Now, this particular case, this is a particular example here that we call a uniform distribution, because the train is no more likely to arrive in 1 minute's time than it is in 2 minutes' time or any other value. Equally likely to occur over that 10 minutes. So I'm going to describe that likelihood as a function, and that function will only be defined over the interval 0 to 10. Okay, no less than 0 minutes, no more than 10 minutes. This, as I said, is a uniform continuous distribution. And it is a probability density function. We'll talk a bit more later about what exactly defines a probability density function. But I'm going to tell you for the time being that that function is 1 over 10. Notice that's a constant function. And I suppose that's because the likelihood of the train is always arriving at any moment in time is always the same. No more likely to arrive early than it is to arrive late. Now, the cumulative distribution function, cumulative, is not telling me how likely it is that the train's going to arrive at any point in time. It's how likely it is the train will have arrived by any point in time. So, if I'm looking at the value of 2, right, 2 minutes after arriving, not how likely it is the train's going to arrive right now, but that it arrives in the first 2 minutes. So what I'm really doing is adding all of those things up, right? As we did previously. In the last video, we looked at cumulative functions, and we used the capital F, remember? The capital F of x. It can be good for quartiles, deciles, and percentiles if I graph it. Right? I can find them off that pretty easy. Now, in this uniform distribution, it's not very hard to find those things anyway, but the cumulative distribution function is really important to us when we are looking at continuous probability density functions. Now, for a function to be a probability density function, I'm just going to call that a PDF now, there are a couple of rules. It has to always be positive, right? I can't ever have a negative probability at any particular point in time of the train arriving. So it must always be positive. And if I graph this, the area between my function and the x-axis must be equal to 1. In some cases that's easy to work out, and in some cases it's a little harder. This might be ringing some bells when I use phrases like the area between the function and the x-axis. It sounds like integrating. And that's exactly right. We are going to integrate my PDF, and when I do that, I get a CDF, a cumulative distribution function. So another way of saying that the area enclosed over that domain is equal to 1 is to say that the value of my cumulative, the integral of my PDF from, right, a definite integral from the start of its domain to the end is equal to 1. Rightio? The probability that my value, x, is between a and b, and for my train, from 0 to 10 minutes, is equal to the integral of, my function was 1 over 10, the integral of that from 0 to 10. Now, for this to be a probability density function, over the full domain has to equal 1. If, however, I just want to find the likelihood of the train arriving in the first 6 minutes, then it is from 0 to 6. If it's the probability that the train arrives somewhere between 3 and 6 minutes after I arrive, it's the integral from 3 to 6. And that's what my example here is asking me to do. I turn up at Acton Town. What's the likelihood that I will wait between 3 and 6 minutes? So the probability that my value, right, how long I wait before the train arrives, is somewhere between 3 and 6 minutes, is the integral of my PDF, which is 1 over 10, from 3 to 6. The integral of 1 over 10 is x over 10. I substitute in the 6 and the 3, subtract those, and that gives me an answer of 0.3, tells me I have a 30% chance of waiting between 3 and 6 minutes. So that's my answer to that question. I'm just going to take up some more of your time now and graph these things. Let's look at these things graphically. So I'm going to graph my probability density function. So I have x, my x-axis tells me how long I wait before the train arrives, and that's going to go from 0 to 10. And my vertical axis is the probability density. It's a bit of a problem to say that's telling me how long, the likelihood of waiting that long, because the probability of the train arriving after exactly 3 minutes is basically 0. Really, that the train will arrive after exactly 3 minutes is virtually impossible after exactly 3 minutes. However, for any given minute, right, if I sort of group some values together, there's a 1 in 10 chance. Now, determining these functions for the time being, not too fussed about. But it is important that that area enclosed there over my domain from 0 to 10 minutes, right, that area has to be equal to 1 square unit, right, because that represents my total probability. and because the train is equally likely to arrive at any point in time, then it's a horizontal line, it's a constant function, and for the area to be equal to 1, then that has to have a height of 0.1, a function value 0.1. That's right. So we've got that. Now, the probability that the train arrives in the first 3 minutes, is this much of that shade, the original shaded area, right, from 0 to 3, and I find the area of that, and it's 0.3. 0.3 chance of the train arriving anywhere in the first 3 minutes. Anywhere in the first 6 minutes is the area of that red rectangle. Now, if I subtract one from the other, right, I'm left with that little shaded area there, which represents the probability of the train arriving somewhere between 3 and 6 minutes. The area of that thing is again 0.3, and that's the answer that I'm looking for. Sometimes that's a good way to calculate the probability. Okay, is to look at a graph of the probability density function and calculate the area between that function and the x-axis over some defined domain. But other times it's more convenient, much more simple, I don't have to draw a sketch, to use a cumulative distribution function, which is the primitive, or the integral, of my PDF. So, again, somewhere between 0 and 10. And I know that after 10 minutes, my cumulative probability is 1, right? After 0 minutes, there's 0 chance of the train having arrived. After 10 minutes, there's a 100% chance the train's arrived, and it's equally likely in between. Of course, if I have a constant function, I integrate it, I get a linear function. Right, we've got this here. So that's my cumulative distribution function. And here I'm not looking for an area, right? Because this is summing all of my areas together. That's what an integral does. So, to find the probability of the train arriving within the first 3 minutes, this is a cumulative figure, then I go along to my 3-minute mark on my x-axis, up until I hit that function, and then back across to my vertical axis and read that off. 0.3. The probability of the train arriving within the first 3 minutes, 0.3. Probability of the train arriving within the first 6 minutes, 0.6 there. And somewhere between 3 and 6 minutes is the distance between those two values there, which is also 0.3. Slightly regretting using these numbers. So, that's how we could use, either graphically or algebraically, a cumulative distribution function to calculate probability for continuous distributions. For a function to be a PDF, it cannot be negative over that domain. Now I say it can't be greater than 1. Well, actually the PDF perhaps could be, I think. But anyway, that's not likely to happen. However, my primitive of the PDF, my CDF, cumulative distribution function, cannot be greater than 1. And in fact, it has to be always increasing, starting at 0 and finishing at 1. Okay, so the integral of my PDF over its domain has to be equal to 1. That's essentially what we've looked at there. There are some new skills there to calculate the probability of a continuous probability density function. Rightio. Any questions, let me know. Our next video is on mean and variance of a distribution. Thanks very much. See you in class.